Hello everyone, this is group H12. In this video, we'll explain implementation of instruction pipeline and its advantages. So what is instruction pipeline? An instruction cycle, also called fetch decode cycle, is basic operational process in which a computer retrieves a program instruction from its memory that determines what actions the instruction decodes and carries out those actions. These are the five stages of instruction pipeline: fetch instruction, decode instruction, fetch operands, execute instructions, write result. So first one is fetch stage. According to the execution instruction definition, the instruction cycle's first step is to capture or fetch the instruction. This instruction in the fetch stage is captured from RAM. This memory is assigned to the processor through various units and registers. They are program counter. It works by pointing towards the next memory line where the next instruction for the processor is stored. Register, memory address, responsible for copying PC content and sending it to the RAM. This is done through the CPU's address pins. Registered, memory data. It takes the responsibility of copying the memory address to the internal register. Register, instruction. It has involvement in the last step of the fetch phase. It is where the instruction is written. The control unit from here copies the content for carrying out the instruction cycle.
The next stage is decode stage. The decoding process allows the CPU to determine what instruction is to be performed so that the CPU can tell how many operands it needs to fetch in order to perform the instruction. The opcode fetched from the memory is decoded for the next steps and moved to the appropriate registers. Typically, the instructions are stored in a particular format that requires some translation so that they can be successfully executed. This decoding is done in the decoding stage. This step evaluates which type of operation is to be performed. If it is a memory operation, the computer checks whether it is a direct memory operation or indirect memory operation. In case of direct memory operation, nothing is done. But in case of indirect memory operation, the effective address is read from the memory. If it is an input output or register instruction, the computer checks its type and executes the instruction.
Now we will go to the execute stage. In a pipeline processor, a pipeline has two ends, the input end and the output end. Between these ends, there are multiple stages such that the output of one stage is connected to the input of the next stage, and each stage performs a specific operation. The data transfer for implementation occurs in two ways, which are as follows. The data is sent from the processor to the memory or from memory to the processor, that is input output data. The second way is it can be transferred to or from peripheral device via a processor, that is IO device transfer. The processor performs essential operations on the information during the execution cycle, and the control consistently requests a change in the data implementation sequence. These two methods are linked together and completes the execution cycle. The execution cycle interprets and performs the operations specified in the instruction accordingly. First of all, the cycle gets started. The processor fetches the instruction. After all, after that it executes the instruction. This cycle repeats again and again, and after the execution of the last instruction, it gets halted. That is, this cycle repeats until all the instructions are executed from the program. After the execution of the last instruction, the cycle gets halted. For example, let us see a real life example that works on the concept of pipeline operation. Consider a water packaging plant. Let there be three stages that a bottle should pass through: inserting the bottle, filling the water in the bottle, and sealing the bottle. Let us consider these stages as stage 1, stage 2, and stage 3 respectively. Let each stage take 1 minute to complete its operation. Now, in a non-pipeline operation, a bottle is first inserted in the plant. After 1 minute, it is moved to the stage 2 where it is filled. Now in stage 1 nothing is happening. Similarly, when the bottle moves to stage 3, both stage 1 and stage 2 are idle. But in pipeline operation, When the bottle is in stage 2, another bottle can be loaded at stage 1. Similarly, when the bottle is in stage 3, there can be a bottle in the stage 1 and stage 2. So after each minute, we get a new bottle at the end of stage 3. Hence, the average time taken to manufacture one bottle is, with in case without pipeline, there is 3 minutes, and with pipeline, it is 1.67 minutes.
The next stage is the memory stage. If data memory needs to be accessed, it is done in this stage. During this stage, single cycle latency instructions simply have their results forwarded to the next stage. This forwarding ensures that both 1 and 2 cycle instructions always write their results in the same stage of the pipeline so that just one write port to the register file can be used, and it is always available. For direct map virtually tagged data caching, the simplest by far of the numerous data cache organizations, two SRMs are used, one for storing and the other for storing tags.
The next is write back stage. In this, during the stage, both single cycle and two cycle instructions write their results into the register file. Note that two different stages are accessing the register file at the same time. The decode stage is reading two source registers at the same time that the write back stage is writing a previous instruction's destination register. This is the example on real silicon. This can be a hazard. That is because one of the source registers being read and decode might be the same as the destination register being written in the write back.
So, let us see the example of implementation of the instruction pipeline. So, the example is a four-segment instruction pipeline unifies two or more distinct segments into a single unit. For example, the decoding of the instruction and the calculation of the effective address can be merged into a single segment. A four-segment instruction pipeline is illustrated in the block diagram given on the screen. The instruction cycle is divided into four main parts, that is, the segment 1, segment 2, segment 3, and segment 4. So, in segment 1, the implementation of the instruction fetch segment can be done using the FIFO, that is, the first in, first out buffer. In the second segment, the memory instruction is decoded and the effective address is then determined in a separate arithmetic circuit. In the third segment, some operands would be fetched from memory. In the fourth segment, the instructions would finally be executed in the very last segment of a pipeline organization.
Now we will discuss some advantages of pipelining. The first advantage here is instruction throughput increases. Throughput is the number of tasks completed in a given time period. So here the number of instruction executed increases in given time period. Secondly, increase in the number of pipeline stages increases the number of instructions executed simultaneously. Thirdly, faster ALU can be designed when pipelining is used. Pipeline CPUs work at higher clock frequencies than the RAM. Lastly, pipelining also increases the overall performance of the CPU.